Hi everyone. Today we're going to continue talking about the lifetime of stars and get into what happens after the stars leave the main sequence, starting to talk about the death of stars, as we call it. So we'll be thinking about the transition out of the main sequence, and we will introduce degenerate matter, what that means, why it's important. We'll look at the different life cycles of a low mass star versus a high mass star and why they're different. And we're going to look specifically at the future of our star, the sun. So a bit of a review. Remember that a protostar, before the star is a full star, it's formed by the inward collapse of that nebula material. The center of the protostar is going to increase in temperature and density to the point where it begins nuclear fusion in the core. This is where we have hydrogen combining to create helium and where the star begins to emit light. What happens is the pressure is generally balanced, so the pressure outwards from the energy emitted compared to the pressure inward of the collapse. When it becomes balanced, we consider that star balanced. And at that point is when the star is a main sequence star. So when that balance occurs from the protostar into the main sequence star, that's the transition right there into the main sequence. So it is a balanced star. The inward and outward pressure is in balance. It's stable. And it's also emitting its own light. So main sequence stars are, again, taking the hydrogen within their core. It is combining, and it is creating helium. So remember that I'm saying the main sequence stars are stable, but they're not perfectly stable. It's changing very slowly, but we know that that hydrogen within the core of the main sequence star is converting into helium. When that happens, you're actually taking 4 hydrogen atoms, and it converts into 1 helium atom. So you're creating less and less and less particles within the core, going from 4 to 1 over and over and over. So you're creating a lot less pressure within the core. What happens is the star is going to slowly start to contract as it loses particles because it's losing pressure within the core. As it contracts, the temperature increases. So as the star gets smaller, the temperature is going to increase. This is going to cause the reactions in the core to happen even faster. So that means the energy flowing outward from the star is going to increase because these nuclear reactions are happening faster. So then the outer layers of the star are going to expand again. The star will become larger and more luminous, and the surface, as it's expanding, will start to cool. So this main sequence region of our HR diagram, remember most of the star's lifetime is actually spent as a main sequence star. Usually 90% of the lifetime of the star, it's a main sequence star. So our young main sequence stars are on the lower edge of the main sequence. Here, the ZAMS is 0 age main sequence, meaning the brand new main sequence stars. And then as the star ages, the star is going to move up and to the right on our diagram along this main sequence path. So as the star ages, the luminosity and the surface temperature are changing to the point where the star is going to continue moving as it ages up and to the right across our diagram. So all throughout, the reason that the star is moving is because it is constantly using up the hydrogen within its core and creating helium. So when the star gets to the point where it's exhausted all of its hydrogen, it's used up all of the hydrogen in the core, and all that's left is now the helium that it created. That is the end of the main sequence portion of the star's life. Remember that the lifetime on the main sequence, so we know it's going to be about 90% of the star's life, but how long will that be depends on the mass of the star. So a very massive star is going to consume fuel much faster, meaning it will have a shorter lifetime. A low mass star is not going to use up the fuel, and by fuel I mean the hydrogen in the core. It's not going to use up that hydrogen as quickly. So low mass main sequence star is going to have a much longer lifetime than a very large, massive main sequence star. So we consider the death of the main sequence to be when that star uses up all of its hydrogen in its core. So the hydrogen within the core of the star is its fuel. When it runs out of fuel, the star is no longer main sequence, and that means that the core will be almost entirely made of helium instead of that hydrogen. Now, it's a lot less helium than there was hydrogen in terms of number of atoms. And the helium core is not strong enough to balance out the force of gravity pushing downward of the star. So what happens is the core will start to contract. It's going to get smaller because it can't withstand that gravitational force. When when the core contracts, the temperature is going to increase. But it doesn't quite increase enough to start fusing the helium that is there. Because the core is contracting, the core temperature is increasing, the outer layers of the star are also going to increase. So what happens is now the outer layers of the star are hot enough to start hydrogen fusion. So the same hydrogen fusion that was happening in the core of the star, due to the fact that the core ran out of hydrogen, the core is going to get smaller. It's going to increase in temperature, which is going to increase the temperature of the outer layers and cause that same hydrogen fusion to begin in the outer layers now of the star. So what happens as this fusion is occurring in the outer layers of the star is the star expands rather rapidly and they become giant stars. So when that fusion is happening in the shell of a star, which is what we call not the core, so the shell of the star is where we have that fusion occurring. The stars are going to get much larger. If you have a medium-sized main sequence star, it'll expand up to a giant size. The larger main sequence stars will expand to become supergiants. So as this is happening, it's the same amount of stuff in the star, but the star is expanding in a very, very large amount. So the volume of the star is going to, the density of the star is going to decrease. So the star becomes a lot less dense. So the star is expanding, and it is made up of many less atoms than it was when the whole star was made of hydrogen. So our giant stars, both the giants and the supergiants, are very, very low density stars. So as the star expands, the star will be moving to the right on the HR diagram. So as the star expands, the temperature is decreasing. So the star is going to move towards the right or towards the lower temperatures and pretty quickly on the diagram. Because the star is increasing quite quickly as that hydrogen fusion begins in the shell of the star is getting much, much, much larger. It's getting very cool. So it stays at about the same luminosity because now we're at these giant and supergiant stars. So because the changes occurring are both temperature and size, the star actually stays at about the same luminosity as it's moving away from the main sequence towards the supergiant or the giant. So the star, from a supergiant standpoint, if you have a large main sequence, really the luminosity is going to stay quite constant. If you have a smaller main sequence star, you might have a little bit of increase in luminosity as the star expands. So depending on where you are, the overall motion is absolutely to the right. However, sometimes the stars do get a bit brighter at this point if they're not as bright to begin with. So now we have the core of our stars. They are completely, or I should say almost completely, made of helium. And the core has started to contract. So remember, the core is contracting. That is causing the temperature increase, which causes the increase in the temperature of the shell of the star, allowing for that fusion in the shell, allowing for the increase in size. So if we look back at the core is going to continue to contract because of trying to balance out that gravity. It's going to become incredibly small, even though the outer layers of the star are becoming giant or supergiant star. The core is very, very, very small. The helium core, it usually becomes so dense that it becomes very, very, very highly compressed. It's not enough temperature for the helium to start fusing the way that hydrogen did. The core continues to contract, becomes as small as it can, to the point where the electrons within the core and within the atoms within the core cannot move. The electrons sort of get stuck at their certain energy levels. So when a gas or an atom is very highly compressed, the electrons will fill up all of the energy levels for each atom, to the point where the atom can't fit any additional electrons, and the electrons can't move from one level to another. So it looks something like this. So here we have a low density gas, a regular gas. We have our electrons. They're on their different energy levels. If we say down at the bottom of the screen is the nucleus, these electrons are free to jump, to move up and down, depending on if they're excited, if they get excited and then jump back down. However, when we have a really high density gas, so like the helium within the teeny tiny core of our star, because it's compressed so much, all of the electrons are squished down to the lowest orbitals, the lowest energy levels, to the point where they can't move. So nothing can move. None of these electrons can make any shifts in energy level. And what we call this is the atom is degenerate. This is when it is so densely compacted that the electrons cannot move. So if this atom were to absorb energy, it could speed up to a higher level if it were to absorb a lot of energy. However, when we are talking about a gas being degenerate or matter being degenerate, we're always talking about gas that is too dense. Gas that is, in fact, so dense that these electrons can't freely move. So this is what is happening in our helium core due to the incredible compression of that core. So our degenerate matter is really interesting because by the time that the helium core becomes fully degenerate, that matter, when it is degenerate, begins to completely resist compression. So it can't be any further compressed. It cannot change. Can't change energies. It can't push any electrons. It can't push against other moving electrons. You can't do anything with this matter. It's actually harder to compress degenerate matter than it would be to compress the toughest steel that we've ever had. So this matter now has been compressed so much that it cannot be compressed any further. It fully resists any further compression. So what that means is the properties of this matter shift. So pressure no longer depends on temperature. Pressure will depend on the speed of the electrons. Our electrons aren't moving. Temperature will depend on the motion of all particles. So adding heat to our degenerate matter, it'll change the speed of the nuclei, but it's not going to affect how the electrons are positioned. So there's no change in the electrons around the atoms, but the atoms themselves can move. So adding heat means the atoms are moving around, but you're not changing anything about the atoms internally. changing the temperature has no effect on pressure of the material. So here we have a diagram. Here's a main sequence star. So it will be about 90% of its life as a main sequence. And then notice the core in the next step gets much smaller, while the actual outside of the star gets much larger. So the photosphere, the outer part of the star is going to be expanding, whereas the core is going to seriously contract. So here we have our tiny core of helium gas, and we have the hydrogen fusion happening in that smaller red shell that would be surrounding that surrounding that core. So what happens next is we know that hydrogen fusion is creating helium. So we know hydrogen fusion has created a lot of helium in our stars. As it's doing this, it leaves behind something that we call helium ash, which is the star's too cool to fuse this helium. Originally, the main sequence star, it's too cool to fuse this helium. Later in its life, if that helium gets hot enough, it will begin the helium fusion. Helium fusion then creates carbon. So as this core is contracting, becoming more and more and more compressed, it's going to grow hotter. And the larger the star, the hotter the core will be able to become. So helium fusion beginning actually depends on the star's mass. So if the star is large enough, this helium fusion will begin due to the compression of the core. So if the star is about 3 times the size of our sun or larger, it's large enough that as the core starts to contract, so now it's a fully helium core, as that core is contracting due to gravity, it will heat up enough to start this helium fusion. And then the helium within the core will start converting into carbon. If the star is not large enough, so think of a star about 3 times the size of our sun or smaller, the core will contract until it is fully made of that degenerate material. So that degenerate material is incredibly dense, it's resistant to further compression, but eventually the temperature is going to rise so much that the helium fusion will start anyway, creating energy with no change in pressure. So the temperature of the gas does not increase with that change in pressure, because remember, with the smaller stars, we're talking about degenerate material. So what we call this, it's called a helium flash. When the temperature increase will cause more and more helium to fuse. And at some point, for just a few minutes, the core of this star that was made of degenerate material will start creating more energy per second, more energy per time than the entire galaxy. And it only lasts for a few minutes. That's why it's called a flash, this helium flash. It's the core of that star is going to be creating more energy per time, per second, than the entire galaxy at the time. What's even cooler is that this doesn't destroy the star. The star survives, even though it's creating more energy than the entire universe. That core is teeny tiny and super, super dense. It is very, very, very small. So this huge output of energy sort of radiates outward throughout the star, and all of that energy released by that helium flash will actually be absorbed by the outer layers of the star. So the energy moves outward from the core of the star, from the center of the star, and the outer layers of the star are going to absorb that energy. So because of this huge helium flash, the core becomes super hot, meaning electrons can jump up to a higher energy level, because the only thing that can happen with our degenerate material is those outer layers can absorb some energy. It takes a huge amount of energy to turn degenerate material back into non-degenerate material. It is this helium flash that does that. So after our helium flash, there's a huge release of energy from the core, and the core is no longer made of that degenerate material, and it's hot enough for the star to begin helium fusion on its own. So our sun, remember, is considered a smaller star. So our sun will go through this helium flash portion. So our sun will have, after being a red giant, and it's going to get warmer, it will eventually become a red giant. As it expands, we know the core of our star will be converting into helium. It will be contracting. That will cause the outside of the star to get larger. We'll have our red giant. Eventually, the core will contract to the point where the core is made of completely degenerate material. Then we will have a helium flash, which will allow then for fusion to begin again inside of our now helium core. But don't worry, we have quite a few billion years before we get to that point. So this bottom line, this x-axis here, is in billions of years. So we have many billions of years before we have to worry about our star leaving the main sequence. So our helium fusion begins in the core, now either in our large stars or our small stars. So the large stars, it happens more naturally. The cool stars have to go through that helium flash process. So you'll notice here on this diagram, we have the helium flash shown just for the smaller stars, so the less bright stars. Here are the brighter stars, which we can assume are larger stars because they're about the same temperature. They do not go through that helium flash portion. So once the helium fusion in our core, in the star's core, begins, the star is again making its own energy. So both in the helium core and in the shell just outside the core that's still experiencing the hydrogen fusion. So the star will begin to send energy outward. Energy will flow outward from the center of the star, especially to balance out the force of gravity, causing the star to contract. So as this energy is flowing outward, the outer layers of the star are going to get warmer because we have our core now creating this fusion. The energy from that fusion is going to radiate outwards to the outer layers of the star. So the star is going to get warmer, especially in the outer layers. So the stars will move after this helium fusion begins. The stars are going to move back towards the left of our diagram because they're getting warmer. Eventually, the core of the star is going to run out of fuel again. So the same way that the star first starts with hydrogen fusion, uses up all the hydrogen, then it starts fusion of helium, the star will eventually use up all of the helium fusion. So what's happening then is as the helium is fusing, it's creating carbon and oxygen. The core of the star is just going to continue fusion of whatever element is there, and it's going to get heavier and heavier each time. So we started with the lightest element, which is hydrogen. Hydrogen fused into the second lightest element, which is helium. Then we go to carbon and oxygen, where the core of the star is going to get heavier and heavier and heavier. We go to neon, we go to magnesium, until the point that the star is creating incredibly heavy elements like iron inside of its core. So really what happens in terms of our HR diagram is the helium gets used up. It's then replaced by carbon and oxygen. When the core is made of carbon and oxygen, it's not going to be warm enough or hot enough to begin fusing, because it takes even more energy to fuse the carbon and the oxygen. So fusion can't occur, the core starts to cool down, and then the core will start to contract. As it contracts, it heats up to the point where that fusion can begin. Then it will be fusing the carbon and the oxygen to the point where the carbon and the oxygen are completely used up. Then the core will be too cool to fuse the next largest element, which is neon. Then the core will contract again. The contraction will cause it to heat up, which allows for the fusion to begin. So it's a cycle that goes on with the core of the star as we're cycling through the fusion of heavier and heavier elements within the star. So on the HR diagram, it actually will create a loop. Here we go. Where the star is going to be moving back and forth or doing sort of a loop-de-loop. As the star, let's see, this guy here right under my laser pointer is where we have the helium fusion beginning. So the helium fusion begins in the core. The star is going to move towards the left of the diagram, and then the star will again move back towards the right of the diagram as it cools down after that fusion. In order for now the carbon in the core to begin fusing, the star has to contract and get larger. And then as the carbon is, it has to contract and get warmer. And then as the carbon is all used up, the star is going to get cooler. As now the core will be made of oxygen, it has to contract and get warmer and back and forth and back and forth. So as the star is going through these heavier and heavier elements, it's going to be doing these zigzags or these loops on our HR diagram.